As a leading cause of death in the US, heart failure is a pressing clinical problem that requires better understanding of the variables that lead to cardiac dysfunction. Among them, measurement of cardiac deformation, especially of the left ventricle, offers important insight. LV deformation can largely be characterized by its compression and twist. A reduction in LV twist is especially an important clinical marker for systolic and diastolic dysfunction, as well as heart failure, which is why numerous cardiac MRI methods are currently in use to measure LV twist. Cardiac phantoms have been in use to quantify and assess mechanical heart function in medical imaging. Our main goal was to design a device that can manipulate a phantom to validate a cardiac MRI technique called DENS. DENS offers a higher spatial and temporal resolution than a conventional cardiac MRI and can provide additional insight.
While there are few commercially available dynamic heart phantoms used for imaging, these are very expensive and only provide data on gross deformation of the left ventricle rather than on specific metrics. A twist-only phantom has been used for dense analysis, and our clinical mentors created an apparatus that allows for compression only. However, neither of these devices allow for both compression and twist, thus being suboptimal devices to validate cardiac imaging techniques. We developed a portable, low-cost, MRI-compatible apparatus that simultaneously compresses and twists a gel phantom using a pneumatic piston cam follower mechanism to generate imaging signals more faithful to left ventricle deformation.
From our SolidWorks rendering of our device, you can see the acetyl plastic dowels or cam followers, which are embedded into the top plate and slide down the track in the shells encompassing the gel phantom. The angle of the track has been optimized to achieve the desired compression and twist. Here is the device twisting and compressing the gel phantom by 1 inch. By using a visual marking on the phantom, the amount of twist was calculated to be 12.5 degrees, which is in the ideal range for a healthy heart. During imaging, the MRI-compatible device is placed directly in the MRI scanner. The electronic Arduino controller, which drives the piston, is placed in the control room and connected to the device through an inlet in the wall. The air compressor is located in an outside room and is connected to the Arduino via rubber tubing. Here you can see our device being imaged in an MRI room at the SFVA Medical Center.
Acquired images of the phantom from MRI spam tagging here showcase simultaneous longitudinal and circumferential strains. These values fell well within LV specifications, demonstrating the device's ability to generate physiologically accurate heart signals. Finally, data from DENS acquisition was extrapolated to analyze three shown in these heat maps. A finite element model was constructed using this data, and it clearly demonstrates that the phantom had undergone a significant amount of simultaneous twist and compression. Overall, this easy-to-operate MRI-compatible phantom heart device can be used by physicians and scientists to validate new imaging technologies such as DENS and ultimately advance the research community's understanding of cardiac disease mechanics.